Usually, when we picture a catastrophic failure, or I guess on the flip side, a really brilliant piece of engineering, we tend to think in macro terms.
Yeah.
We picture a massive structural collapse, a towering skyscraper, maybe an explosion.
Right. The big flashy stuff.
Exactly. But so often, the line between absolute perfection and total disaster, it comes down to a space no thicker than a single sheet of paper. It literally comes down to the exact millimeter where two surfaces meet.
Yeah, that microscopic
Right.
interface.
Every single time two things touch, whether that is like deep inside a car's engine block on the launch pad of space shuttle, or even just right under your fingertip as you adjust a dial on your dash, there's this huge potential for massive energy loss, catastrophic failure, or, truly elegant engineering.
It's basically the ultimate hidden world. I mean, when a mechanical interface is working perfectly, you don't even know it's there. You only notice these connections when they fail or when they fight back.
Yeah, perfectly said.
And the physics governing these really microscopic interactions, they shape our entire macro level world in ways we rarely appreciate. At least until something goes terribly wrong.
Which is exactly why we're doing this. Our mission for you today is to explore the past, the present, and the future of how things connect. We're going to journey from the atomic level energy drain of basic friction to the high-tech, touchless revolution of magnetic gears.
Which is wild, by the way.
So wild.
Mm.
And finally, we'll look at the human element, how we desperately need physical contact to operate machines safely and how engineers have to, well, sort of idiot-proof those interactions.
Yeah, designing physical safeguards to save us from ourselves.
Exactly. So we've compiled a big stack of sources for this deep dive. We're looking at global tribology reports, quantifying energy loss, NASA technical documents on the Challenger disaster, automotive safety studies, and this really fascinating Japanese manufacturing guide on mistake proofing.
It's a great mix of material.
Okay, let's unpack this. Before we can even talk about how to connect things perfectly, we really have to look at the invisible enemy that is constantly stealing our energy. If you go for a long drive, you pull into your garage and put your hand near the hood of your car, you feel that intense heat radiating off the metal.
Right, it's baking hot.
Yeah. And a huge portion of that heat is literally just wasted energy from parts rubbing together inside the engine.
Which brings us right into the realm of tribology.
Tribology, that's a great word.
It really is. It comes from the Greek word tribo, which means to rub. It's the study of interacting surfaces in relative motion. So it encompasses friction, wear, and lubrication.
Okay, so things rubbing against other things.
Essentially, yeah. And while it might sound like a highly specific, maybe even niche subfield of mechanical engineering, the global implications are actually staggering. We have data here from a highly influential 2017 study by Kenneth Holmberg and Ali Erdemir.
Right, and that built on some foundational work from the 1960s, right? The JOST report.
Exactly. They were attempting to quantify the real macroeconomic impact of friction and wear. And the numbers they found are, honestly, hard to wrap your head around.
Yeah, when I saw the stats in the source material, I had to read it twice. According to their calculations, approximately 23% of the world's total energy consumption originates from tribological contacts.
Think about the scale of that for a second. Nearly a quarter of all the energy we produce globally is tied up in dealing with this one physical phenomenon.
It's insane. 1 in every 4 barrels of oil extracted, 1 in every 4 wind turbines spinning, 1 in every 4 solar panels. All of that energy is entirely dedicated to overcoming friction or repairing the damage caused by it.
Yeah, the study breaks down that 23%, actually. 20% is used purely to overcome the physical resistance of moving parts sliding against each other, just pushing through the friction.
And the other 3%?
The remaining 3% is the energy required to remanufacture worn parts. So replacing spare equipment that degraded just because of that constant wear and tear over time.
It's like walking through knee-deep mud. The calories you're burning aren't going into moving you forward. They're just going into fighting the medium around you.
That is a perfect analogy.
But, I mean, if a quarter of the world's energy is just lost to things rubbing together, why haven't we solved this yet? We've been building machines for centuries.
Because we are fighting fundamental physics at a microscopic scale. It's not a simple fix. But if we look at the environmental and economic impacts outlined in the study, the potential savings, if we do improve things, are monumental.
Right.
The largest short-term energy savings are envisioned in the transport sector, where we could see a 25% savings, and power generation, where we could see a 20% saving.
Well, that makes intuitive sense to me. Transport involves engines, axles, wheels, just constant high-velocity motion.
Yeah, right. Lots of moving parts.
And power generation relies on massive turbines spinning continuously under these really incredible loads.
Absolutely. If we were to implement advanced tribological technologies across those sectors, things like advanced surface texturing, diamond-like carbon coatings, or newly engineered synthetic lubricants, the short-term global savings are huge.
How huge?
We could reduce carbon dioxide emissions by as much as 1,460 million tons of CO2 equivalent. Economically, they project that translates to 450,000 million euros in short-term savings.
Wow. Almost €500 billion just by making industrial interfaces slightly more slippery.
Basically, yeah. And the long-term projections are even wilder. As these technologies scale and compound over time, the reduction could reach over 3,000 million tons of CO2 and nearly €1 trillion in savings.
€1 trillion? That's wild. But to understand why it's so hard to capture those savings, we really need to zoom in on the physical mechanics of that energy dissipation. We have this excerpt here from an article in Physics Today that dives into what is actually happening down at the molecular level.
Right, because in most heavy-duty applications, we aren't just rubbing two dry blocks of metal together. There is almost always a lubricant involved. The article discusses this concept called viscous dissipation.
Viscous dissipation. Okay, break that down for us.
So to understand it, we have to map out the transition from fluid film friction to boundary friction. In a really optimal engineering scenario, you have fluid film friction.
Meaning?
Imagine two metal surfaces separated entirely by a very thin liquid film, like a highly engineered synthetic oil. When those metal surfaces slide past each other, they aren't actually making physical contact.
Oh, I see. They're essentially hydroplaning. The oil is taking all the abuse.
Exactly. They are surfing on the oil. But that abuse still requires energy to overcome. The energy dissipation in this fluid film state is entirely due to the viscosity of the fluid itself. The fluid naturally resists being shear.
Okay, that makes sense.
The Physics Today article lays out the mathematical relationship. If you have a sliding velocity, let's call it v, moving across a roughly uniform fluid film of thickness d, with an effective viscosity we'll call eta, the surfaces experience a very specific shear stress.
Okay, let me translate that into English for a second. So the friction in that perfect fluid film state depends linearly on three things.
Yeah.
How fast the surfaces are sliding past each other, how thick the layer of oil is, and how inherently thick or sticky that oil is.
That's a solid summary, yeah.
So if you increase the speed, you increase the friction. If you make the oil stickier, you increase the friction.
Exactly. But here's the catch: machines in the real world do not operate in a perfect continuous state. They start, they stop, they experience sudden shock loads.
Right, it's not a perfect laboratory condition.
Far from it. When you start an engine from a cold block, or when a massive torque load is suddenly applied to a gearbox, or if the sliding velocity just drops too low to maintain that hydrodynamic pressure, the fluid film gets physically squeezed out.
Like squeezing toothpaste out of a tube.
Kind of. The film thickness, that D variable, drops to 0 in localized spots. And that is when you transition out of fluid film friction and cross over into the danger zone. Boundary friction.
And boundary friction is where the real damage happens, right?
Yeah.
That's when the metal is actually making physical contact.
Oh, it goes further than just making contact. At a microscopic level, you have to realize no surface is perfectly flat, even polished steel. Under a microscope, they are covered in these jagged, microscopic peaks and valleys known as asperities.
Asperities, okay.
When that fluid film breaks down, the asperities of the top surface violently collide with the asperities of the bottom surface. And due to the immense localized pressure, these microscopic peaks actually cold weld together momentarily.
Wait, they weld together, like they bond.
Literally weld, yes. The pressure is so high it fuses the metals, and then, because the sliding motion continues, those microscopic welds are instantly and violently torn apart.
Oh, wow. That sounds incredibly destructive.
It is. This microscopic welding and tearing creates intense localized heat. It physically shears away tiny fragments of the metal, which then become abrasive particles just floating in your oil.
Which just causes more wear.
Exactly. And it creates a massive spike in energy consumption. That specific phenomenon, that tearing of asperities, is the wear that Holmberg and Erdemir noted takes up 3% of global energy just to replace.
So if 20% of the world's energy is lost to these asperities colliding, and liquid oils can just get squeezed out under high pressure or low speeds,
Hmm.
why are we still relying on them? Aren't there better ways to separate those metal surfaces when liquid fails?
There are, definitely. And that brings us to the really fascinating world of solid or dry lubricants. When we look at the effects of friction on equipment, a report from Muscle Products Corporation lays it out clearly. Internal friction increases heat and mechanical resistance, which reduces fuel efficiency, accelerates wear on pistons and camshafts, and just leads to premature failure. We use oil and grease to mitigate this, but there are environments where liquid oil is either entirely useless or actively dangerous.
Yeah, the source material outlines 4 commonly used solid lubricants that solve problems liquids simply cannot. The first one is graphite,
Which is super common.
right? Most people associate graphite with pencil lead, but it's used heavily in air compressors, the food industry, and railway track joints. The application that really caught my eye, though, was its use in locks. It is incredibly common for lubricating keyholes and internal lock tumblers.
It seems counterintuitive at first glance, doesn't it? We are conditioned to think that if a door hinge squeaks, we spray a liquid hydrocarbon on it.
Grab the WD-40.
Exactly. Therefore, if a lock is sticky, people think they should squirt liquid oil into the keyhole. But doing that is a guaranteed way to completely ruin the lock.
Because the liquid oil is wet, right? And in an open environment, it acts like a trap. It just catches ambient dust, dirt, sand, and microscopic metal shavings.
Yep. It turns into a magnet for grime.
And over time, that creates this thick, highly abrasive sludge. Instead of lubricating, it actually jams the intricate, tightly toleranced pins inside the lock cylinder.
Graphite avoids this entirely because it's a dry powder. At a molecular level, graphite is composed of lamellar structures.
Lamellar, what does that mean?
Essentially, they are stacked sheets of carbon atoms. The bonds within each individual sheet are very strong, but the bonds between the stacked sheets are very weak van der Waals forces.
Oh, I see. So the sheets just slide off each other, kind of like a freshly opened deck of playing cards spreading across a table.
That's a perfect visual, yeah. The graphite powder coats the metal surfaces of the lock pins and provides this low-friction sliding layer, allowing those atomic sheets to shear easily without attracting or holding on to any ambient grit.
That makes so much sense.
It's also exactly why graphite is frequently used in the internal moving parts of firearms, particularly by the military in sandy or desert environments. A wet oil in a desert would instantly turn into abrasive mud, jamming the weapon.
But graphite has its limits, right? The next dry lubricant on the list is molybdenum disulfide, or MOS2. Where do we use this?
MOS2 is critical for constant velocity joints in vehicles, but its most vital mission-critical application is actually in space vehicles.
Because space is a hard vacuum. I mean, you can't just have an oil pan sloshing around on the outside of a satellite.
In a hard vacuum, liquid lubricants are an absolute nightmare. They have a vapor pressure, meaning without atmospheric pressure holding them in a liquid state, they will literally boil off into a gas.
Spontaneously vaporize.
Yep. Or, on the flip side, they can freeze solid in the extreme cold of orbital shadow. And worse, that outgassing vapor can condense onto sensitive optical lenses or solar panels, which would instantly blind or cripple a multi-billion-dollar piece of hardware.
Oh, wow. That would be a very expensive mistake.
Definitely. Molybdenum disulfide, however, remains completely stable. It provides robust lubrication in a vacuum environment where liquids would just fail completely.
That's incredible. And we have hexagonal boron nitride, which the source refers to as white graphite.
Right. Its molecular lamellar structure is very similar to graphite, but it possesses totally distinct thermal properties. It is heavily utilized for extreme high-temperature applications.
So like furnaces.
Furnaces, yes, or aerospace components that reach temperatures that would instantly vaporize or ignite a traditional hydrocarbon oil. You use hexagonal boron nitride for those. It's also used a lot as a mold release agent in high-temp manufacturing.
The final one listed in the source is tungsten disulfide. It has similar usage to MOS2, but the source notes it's significantly more expensive, so it's usually reserved for very specific, highly specialized, dry lubricated bearings.
Yeah, it's the premium stuff.
So we have this massive, complex arsenal of materials, liquids and solids, designed specifically to stop things from gripping each other. But we don't always want things to slide. I mean, what happens when we have to make them grip? You can't build a wind turbine or a skyscraper out of perfectly lubricated sliding plates.
And this is the grand dichotomy of mechanical engineering. Half of the discipline is fighting friction tooth and nail, and the other half relies on it absolutely.
Let's talk about fasteners then. According to a document from Eastern Illinois University, complex structural engineering, wind turbines, railroad bridges, massive infrastructure relies heavily on bolted joint assemblies.
Right, because the entire intent is that once these components are brought together, they remain static forever. They should never move.
When you look at a bolt, you might just see a piece of threaded metal filling a hole. But the physics of how a bolt actually works are entirely based on friction and tension.
Yeah, the EIU report notes that when a bolt and nut are tightened down, they actively pull the two joining surfaces together, creating what's called a massive clamping force.
You are actually stretching the bolt slightly.
Yes. You are pushing the metal of the bolt into its elastic region, essentially turning it into a very stiff tension spring. The thread pitch acts like an inclined plane wrapped around a cylinder.
And it is the friction between the threads of the bolt and the nut, combined with the friction between the clamped surfaces, that holds that tension and prevents the assembly from just vibrating loose.
But vibration is the absolute enemy of static friction. If a railroad bridge is vibrating every time a multi-ton train rolls over it, that dynamic vibration introduces microscopic transverse slip.
Transverse slip, basically wiggling back and forth.
Exactly. It's constantly trying to overcome the static friction holding the nuts in place.
And mitigating that transverse slip is where washers come in, right? We have a source from Monroe Aerospace that categorizes an array of washers. You have flat washers, which simply distribute the load so the bolt head doesn't crush into the base material. But then you have internal and external locking washers.
Locking washers are super interesting. They are specifically designed to alter the physical interface to actively fight vibration. They have these angled teeth or a spring tension that physically bites into the metal surfaces.
So they're digging into the metal.
Yes. They mechanically increase the friction and provide physical resistance to rotational loosening. Monroe Aerospace also lists sealing washers, which keep fluids out of the joint, and nylon washers, which provide a buffer to prevent galvanic corrosion between dissimilar metals.
It's just incredible to think about a massive structure like a wind turbine, hundreds of feet in the air, enduring massive wind shear. The only thing keeping the blades attached to the hub or the tower attached to its foundation is the microscopic static friction clamped down by these bolted assemblies.
It's all just friction holding the world together.
But it relies on the environment staying relatively constant. You tighten a bolt, or you seat a seal, assuming the physical properties of the materials won't change. But what happens when the environment forces a change in the physical interface itself?
And that brings us to one of the most sobering case studies in modern engineering history. We have to look at what happens when a critical interface is subjected to environmental extremes it was simply never designed for.
Yeah, we are looking at the findings of the Rogers Commission report. This was the official presidential commission tasked with investigating the 1986 Space Shuttle Challenger disaster.
A truly tragic event.
The commission found that the immediate physical cause of the accident was a failure in the O-rings sealing the aft field joint on the right solid rocket booster.
Right. And for those listening who might not work with them, an O-ring isn't just a simple rubber donut. It's a highly engineered mechanical gasket designed to be seated in a groove and compressed between two parts, creating a dynamic seal.
In the case of the space shuttle, the solid rocket boosters were too large to be transported in one piece, so they were assembled in segments.
Right. Yes. And between these massive cylindrical segments, you have a field joint, specifically a clevis and tang joint. Inside that joint are two massive O-rings, a primary and a secondary made of a synthetic rubber compound called FKM, or VTON.
And their sole purpose is to prevent the pressurized, unimaginably hot gases of the solid rocket exhaust from escaping through the joint.
But on that specific day, the seal failed. The report says it caused pressurized hot gases and eventually a jet of flame to blow by the O-ring. The flame acted like a blowtorch, contacting the adjacent external fuel tank and causing a total structural failure of the vehicle.
So the mechanical interface failed. But the core question is, why did it fail at that exact moment?
We have a NASA technical report titled O-Ring Sealing Verification for the Space Shuttle Redesign that explains the physics of this specific seal. The report states that the resiliency of the O-ring is found to be extremely sensitive to the effects of temperature. This is crucial. The seal was designed to be pressure-assisted.
Wait, meaning the pressure from the rocket ignition actually helps the seal work better.
Exactly. When the rocket ignites, the massive internal pressure pushes the rubber O-ring into the corner of the groove, forcing it to fill the microscopic gaps. However, for that pressure assistance to occur, the rubber must maintain physical contact with the sealing surface at all times,
Even when the metal is moving.
especially when it's moving. As the metal of the rocket booster shifts, expands, and flexes under the immense pressure of ignition, a phenomenon known as joint rotation, the rubber O-ring has to instantly spring back or track that deflection to keep the gap plugged.
The NASA report notes that as long as physical contact is maintained, pressure assistance induced instantaneous sealing. But that resiliency, that ability to spring back instantly to fill the opening gap, is a physical property of the polymer chains within the rubber, and rubber chemistry is deeply affected by cold.
Which brings us to the operational reality of launch day. The temperature in Florida was exceptionally cold. It was between 28 and 29 degrees Fahrenheit.
Below freezing.
Below freezing. Prior to this, the absolute coldest launch they had ever attempted or had solid data for was at 53 degrees Fahrenheit.
That is a huge difference, a 25-degree drop below the previously proven safe operational limit.
Right.
If you keep a rubber band at room temperature, you can stretch it, let it go, and it snaps back instantly. It has high resiliency. But if you put that same rubber band in your freezer overnight and try to stretch it, it's completely rigid. If you bend it, it doesn't snap back. It stays bent or it shatters.
Because as polymers get colder, they approach what's called their glass transition temperature. The chains lose their mobility.
And that is precisely what happened to the FKM O-rings on the launch pad.
The freezing temperatures caused the rubber to become stiff and lose its resilience. When the solid rocket ignited and the metal joint expanded outward, the rubber was too sluggish to track the expanding gap.
So a microscopic pathway opened up.
Just for a fraction of a second, but that was enough. The pressurized hot gas found its way past the primary and secondary seals.
But, mechanical interfaces don't exist in a vacuum. They are designed, tested, and greenlit by humans. The Rogers Commission report didn't just point to the stiff rubber. They identified a catastrophic systemic human failure. They actually called it an accident rooted in history.
This is where physical friction intersects with organizational friction. The report details that as early as 1977, nearly a decade before the disaster, managers at NASA and the contractor that built the boosters, Morton Thiokol, were aware of design flaws in the O-ring joint.
So they knew it had a high potential for catastrophic failure.
They did. And on the eve of the launch, engineers at Morton Thiokol, specifically Roger Boisjoly and Alan McDonald, fiercely argued against launching. They presented data showing the O-rings would not seal properly at those unprecedented cold temperatures. They literally pleaded for a delay.
But there was immense political and organizational pressure to maintain the launch schedule, wasn't there?
Massive pressure. The communication breakdown was profound. Morton Thiokol management, succumbing to pressure from NASA, famously told their VP of engineering to take off his engineering hat and put on his management hat, actively overriding the safety concerns of their own experts.
That is just heartbreaking. The story of how the physical cause was actually proven during the investigation is legendary, though. You had the brilliant physicist Richard Feynman on the commission. He suspected the cold was the trigger based on his knowledge of polymer physics.
But he was an outsider. Facing a wall of institutional deflection, he needed internal data.
Right. And he received a crucial nudge from General Donald Kutina, another commission member. Kutina cunningly asked Feynman a seemingly innocent question about the effect of cold on O-ring seals, subtly highlighting the freezing temperatures on launch day versus the 53-degree previous record.
The incredible twist, revealed much later in a 2013 BBC documentary, was how Kutina knew exactly where to point Feynman.
It was astronaut Sally Ride, right?
Yes. She was also on the commission. She had secretly provided Kutina with internal NASA test results data that management was likely trying to minimize, proving that the O-rings became stiff and compromised when subjected to cold.
She essentially acted as a whistleblower to ensure the physics couldn't be buried by bureaucracy.
And it culminated in Feynman's famous demonstration during a televised hearing. He took a piece of the O-ring material, clamped it with a C-clamp, and dropped it into a glass of ice water.
Just right there on television.
Right there. After letting it chill, he undid the clamp. The rubber remained pinched. It didn't spring back. He proved, visually and undeniably to the American public, that the physical interface lost its integrity under the environmental conditions of launch day.
It is a chilling realization. You have millions of pounds of explosive thrust, the absolute pinnacle of cutting-edge aerospace engineering at the time, and the entire endeavor relied on a piece of synthetic rubber having enough physical resilience to plug a microscopic gap.
It's terrifying.
That disaster really highlights the inherent vulnerability of physical contact. The rubber had to physically touch the metal. If physical interfaces are that sensitive to temperature, wear, and environmental drift, why do we even mandate physical contact in critical systems?
Well, that is the exact question driving a massive paradigm shift in advanced mechanical engineering today. If physical contact is the root cause of friction, wear, and catastrophic failure, the logical solution is to remove the physical interface entirely.
Welcome to the touchless revolution. Let's look at the research from the UT Dallas Research Labs on magnetic gears. The core concept is that they perform the exact same function as traditional mechanical gears. They transform power,
Right.
they take low-speed, high-torque rotation and convert it into high-speed, low-torque rotation.
Okay.
But they achieve this power transmission using invisible magnetic fields instead of mechanically interlocking metal teeth.
There are several architectures being developed, such as the radial flux coaxial magnetic gear and the cycloidal radial flux magnetic gear, but the underlying physics relies on the modulation of magnetic flux.
How does that actually look physically?
Typically, you have an inner rotor lined with alternating permanent magnets, an outer rotor lined with permanent magnets, and a stationary ring of ferromagnetic steel pole pieces situated in the air gap between them.
I'm trying to picture the mechanics.
It's akin to an epicyclic or planetary gear train. The stationary pore pieces modulate the magnetic fields emitted by the inner and outer rotors. By carefully designing the number of magnet pole pairs on the rotors and the number of steel pole pieces, the magnetic fields couple together across the air gap, but at a specific gear ratio.
Oh, I get it. So it's like having a really powerful magnet under a glass table and using it to move a heavy piece of steel around on top of the table. They're locked together by this invisible force, but there is actual physical space between them.
That's a great way to visualize it.
We're just scaling that up to industrial heavy-duty applications. So what are the concrete advantages of doing it this way instead of just using metal teeth?
The advantages over traditional mechanical gears are profound, as the Wikipedia source notes. First and foremost, wear is virtually eliminated from the power transmission components.
Because they aren't touching.
Exactly. The only physical friction occurs at the standard bearings supporting the rotor shafts. There are no mating contact surfaces of gear teeth grinding against each other.
Which means no boundary friction, no asperities colliding, and no need for complex liquid oil baths or dry lubricants between the gears.
Exactly, which drastically reduces maintenance and significantly reduces acoustic noise and vibration. Furthermore, because the coupling is magnetic, the gear ratios can potentially be changed by altering the magnetic field properties rather than physically swapping out metal gear sets.
But the advantage that genuinely changes the game, in my opinion, is the inherent safety feature. The source notes they provide a shear-proof or overload-proof mechanical coupling.
This is a critical distinction in mechanical engineering. In a traditional mechanical gearbox, if something jams the output shaft, or if an external force applies a torque that vastly exceeds the design limits, the kinetic energy has nowhere to go.
The teeth just snap off.
Right. The metal teeth of the gears will shear off. The gearbox will literally shatter itself, resulting in total failure and potentially dangerous shrapnel.
But with a magnetic gear, if a massive overload hits the system, what actually breaks?
Nothing breaks. The magnets simply slip. The magnetic coupling force acts as an inherent torque-limiting clutch. If the applied torque exceeds the maximum magnetic coupling force, the inner and outer rotors just slip past one another smoothly without any physical damage.
That is brilliant.
And once the overload condition is removed, the magnetic poles realign, and the gear immediately resumes normal operation. It provides an infinite capacity for non-destructive overload.
It's basically built-in mistake proofing. Now, let's take that concept of magnetic fields crossing empty space and apply it to an environment where physical seals are a nightmare. The vacuum chamber.
Oh, this is a great application.
We talked earlier about how terrible dynamic seals and O-rings are for space and vacuum applications due to outgassing and temperature sensitivity. We have a document from UHV Design detailing magnetic coupling in vacuum manipulators.
This technology solves the dynamic seal problem permanently for enclosed high vacuum systems. In applications like semiconductor manufacturing, nanotechnology fabrication, or thin film deposition, you frequently need to move a sample or manipulate a tool inside a high vacuum chamber.
Right. But the motor driving that motion needs to remain outside the chamber in the normal atmosphere.
Historically, to achieve that, you had to drill a hole in the wall of the vacuum chamber, run a spinning metal shaft through it, and try to seal that moving shaft with highly specialized lubricated bearings or dynamic rubber O-rings.
And as we've established, O-rings can stiffen and fail, and lubricants will outgas, ruining the vacuum.
With a magnetic coupling, you eliminate the hole entirely. The motion is transferred through a completely solid, continuous, non-magnetic barrier. It's typically a thin-walled stainless steel tube or a ceramic wall.
So no hole, no seal needed.
Exactly. The magnet assembly on the atmospheric side is driven by a motor, and the corresponding magnet assembly on the vacuum side follows it precisely. The drive force is transferred entirely by the magnetic field penetrating the solid wall.
So there's no dynamic seal whatsoever. No rotating shaft physically penetrating the chamber walls.
None. The UHV source outlines exactly why this matters so much. No dynamic seals mean no friction-induced wear on a sealing surface, no outgassing from lubricants, and zero risk of vacuum leaks. It provides an ultra-clean, contactless drive mechanism.
I imagine in semiconductor manufacturing, that is paramount. A single microscopic flake of metal sheared off an asperity or a tiny droplet of oil from a sliding interface can contaminate an entire silicon wafer, right? That ruins millions of dollars worth of microchips.
Exactly. The source also notes it's heavily used in cryogenic and high-temperature environments. Those are the exact environments where rubber seals cross their glass transition temperature and fail, or where liquid oils boil and vaporize.
We are replacing vulnerable physical chemistry with fundamental invisible physics. And apparently, the magnetic fields themselves are highly contained. The document notes that at a distance of 50 millimeters from the drive, the stray magnetic field is typically less than 200 milligauss.
Which is tiny.
Yeah, that's less than half the strength of the Earth's natural magnetic field, so it won't interfere with the delicate electron microscopes or deposition instruments operating inside the chamber.
It really represents a remarkable evolution in engineering thought. We spent centuries, from the dawn of the Industrial Revolution onward, perfecting mechanical gear teeth, developing incredibly complex synthetic fluid films, and formulating resilient polymer seals just to manage and mitigate friction.
And now we're just bypassing it.
Right. For our most critical applications, we are bypassing the physical interface entirely. We are using invisible magnetic flux to do the exact same mechanical work across solid, impenetrable barriers.
It's an incredibly elegant solution for machines. Zero friction, zero wear, touchless interfaces. But here is where we have to pivot. For machines, the holy grail is zero friction, zero touch. But that logic completely falls apart when you put a human on the load.
Oh, absolutely.
When we transition away from machine-to-machine interfaces and look at human-to-machine interfaces, we find that we don't want a touchless void. Humans desperately need friction. We crave tactile feedback.
You really do.
Which brings us to the great debate in modern automotive design. Physical buttons versus touch screens.
This is a textbook example of how optimizing an interface for engineering elegance or aesthetic minimalism does not equate to optimizing it for human cognition.
We have a fascinating 2020 study conducted by the Swedish car magazine Bilagar. They designed a rigorous comparative analysis testing drivers' ability to perform tasks using traditional physical buttons versus those using modern touchscreen-heavy infotainment systems.
And their methodology was solid. They didn't just ask people what they preferred, they put them in cars, had them drive at a constant speed, and timed exactly how long it took to perform specific tasks.
And the sleek, futuristic touchscreens performed terribly.
Right. The disparity was massive. The data showed that drivers required roughly 4.6 times more time to perform basic, everyday tasks on a touchscreen compared to performing those exact same tasks in a car equipped with physical controls.
4.6 times longer. That's huge. Like turning on the radio to a specific station, adjusting the climate control by a few degrees, or turning on the heated seats.
Yes, the basic stuff you do every day.
I want to frame that in the context of driving at highway speeds for you. If you are traveling at 65 miles an hour and a task takes you 1 second with a physical dial, your car travels about 95 feet. If that same task takes you nearly 5 seconds hunting through menus on a flat touchscreen, you have traveled the length of a football field and a half.
And crucially, your eyes are not focused on the road for that entire distance. The study explicitly states that this additional time spent looking at a screen significantly increases the cognitive load and the inherent risk of accidents.
Why are our brains so bad at touchscreens while driving?
It's the underlying neurology. Our brains have evolved to process tactile information almost instantaneously, entirely bypassing the need for visual confirmation. The study highlights three key cognitive advantages of physical buttons.
Okay, what's the first one?
The first is tactile feedback. A physical button provides immediate, undeniable physical confirmation. You can feel the textured edge of the volume dial, you can feel the mechanical detent as it clicks into place, all without needing to divert your visual attention from the road.
Which is physically impossible with a flat pane of glass. Think about trying to type a long, complex email on your smartphone's flat glass screen without looking at it, versus typing on a chunky mechanical computer keyboard.
Right, on the glass, your fingers drift.
Exactly. You have zero physical indication of whether you hit the A or the S. But on a mechanical keyboard, your fingers physically register the raised edges of the keys, the depth of the press, and the spring resistance.
That leads directly to the second advantage, muscle memory. With regular use of physical controls, drivers develop spatial familiarity. You learn precisely how far down to reach, what the knob feels like, and how many clicks correspond to a specific temperature change.
And that spatial awareness significantly reduces the cognitive load, right? And the time spent interacting with the system. You just reach out, turn the volume down, and keep your eyes locked on the brake lights of the car in front of you.
Exactly. And the third advantage they list is operational reliability. Buttons don't care if you have greasy smudges on your hands. They don't get washed out by bright sunlight glare.
Oh, that's a good point.
They don't suffer from a lagging software update that freezes the climate control app while you're driving in a snowstorm.
Taking away the physical interface really forces the human brain to rely heavily on visual processing. You have to undergo visual saccades. Those rapid eye movements to find the specific icon on the screen. You have to look to guide your finger accurately, and you have to look again to confirm that the screen actually registered your capacitive touch.
You are actively stealing visual cognitive load away from the primary high-stakes task, which is safely operating a 2-ton kinetic vehicle.
Automakers obviously love screens, though. They are infinitely cheaper to manufacture than wiring harnesses and individual switches, and they look incredibly futuristic on the showroom floor.
But human biology is actively rebelling against them. In fact, we have a paper from ArcCiv discussing the design of mid-air haptic gesture-controlled user interfaces for cars. If the industry must move toward touchless or screen-based systems, researchers are realizing they have to artificially inject the friction back into the experience.
The paper notes that if users are performing gestures in mid-air to control the vehicle's systems, like, say, waving a hand to skip a song, they demand sensory feedback. The researchers report that users heavily preferred haptic sensations that were dynamic.
Meaning the feedback changed according to the system state. Crucially, they preferred sensations that provided a clear, undeniable confirmation feedback after an action was performed.
Wait, how do you provide physical feedback in midair?
They utilize technologies like ultrasound phased arrays. By focusing ultrasonic sound waves, they can create localized nodes of acoustic radiation pressure in midair.
That sounds like science fiction.
It kind of is. When your hand passes through that node, it physically depresses the mechanoreceptors in your skin, artificially projecting the physical sensation of a click or a tactile boundary onto your hand without you actually touching anything.
That is wild. They're spending millions of dollars in advanced acoustic R&D to simulate the exact physical sensation of a 90-cent plastic button, just because the human brain simply will not trust an interface without that friction.
It perfectly illustrates the central tension of modern engineering. We cannot divorce the design of a system from the biological reality of the operator.
Which brings us to the final evolution of this concept. If humans are so deeply reliant on physical cues and simultaneously so prone to distraction, fatigue, and error when operating complex machines, how do we bridge that gap?
How do we save us from ourselves?
Right. How do we design physical interfaces on the manufacturing floor that actively protect us from our own humanity? Enter the art of idiot-proofing, or as it's formally known in engineering circles, poka-yoke.
Poka-yoke is a Japanese term that translates directly to mistake-proofing, or the prevention of inadvertent error. It was pioneered in the 1960s by an industrial engineer named Shigeo Shingo.
And it became a foundational pillar of the highly renowned Toyota production system.
Yes, we have a brilliant guide here from China Manufacturing Consultants, written by Renaud Angeron, detailing practical examples of mistake-proofing on the factory floor.
And the core philosophy of poka-yoke, as defined by an expert named Michel Baudin in the text, is uncompromising. There are 3 strict rules. First, it's all about people. It's not about a machine running complex self-diagnostics. It's about altering the physical environment to make human error physically impossible.
Second, a true poka-yoke works 100% of the time. If a device or a warning light reduces human error by 95%, that is useful mitigation, sure, but it is not a poka-yoke. A true poka-yoke must flow logically from the physical geometry or mechanics of the design.
And third, and perhaps most importantly in a fast-paced environment, it must not add work for the operator.
Because human nature dictates that if a safety device requires an extra cognitive step or slows a worker down when they have a quota to hit, that safety device will inevitably be bypassed, taped over, or disconnected.
Exactly. The safety must be inherent to the operation itself. It has to be seamless. Let's walk through some of the physical examples from the CMC HubSpot document, because this is where elegant engineering meets human psychology.
Let's start with example 1, the die set. In manufacturing, a die set is a heavy piece of tooling used in a press to punch holes or stamp shapes into a metal workpiece. You have a top die and a bottom die.
Okay, pretty straightforward.
But if a tired or distracted worker accidentally places the top die on backwards, say, rotated 180 degrees, and activates the multi-ton press, the male pin punches won't align with the female holes.
Which would ruin the workpiece.
It ruins the workpiece, and it catastrophically damages the incredibly expensive die set.
So how do you prevent a human from putting it on backward? You don't write a strongly worded memo. You don't put up a yellow warning sign that they'll eventually just ignore. You change the physical interface. The poka-yoke solution is simply to modify the steel guide pins that align the two halves.
Right. You make one guide pin large in diameter and make the other guide pin small.
By altering the geometry, it becomes physically impossible to assemble it incorrectly. The large pins simply cannot fit into the small hole. The interface itself acts as an absolute physical barrier to the error.
It's exactly like putting a SIM card into your phone or plugging in a 3-prong grounded electrical outlet. You don't need a user manual to tell you which way the plug goes in.
Right, it only goes in one way.
The physical interface is the instruction manual. The geometry forces compliance.
If we look beyond simple geometry, we can use smart interfaces, like sensors. Example 5 discusses limit switches. Imagine a workpiece needs to be seated perfectly flat in a fixture before a high-speed drill press activates.
Okay.
You install physical limit switches, essentially small mechanical arms connected to electrical contacts underneath the fixture.
The circuitry is brilliant here. If the part is seated correctly, its mass presses down all the limit switches, closing the circuit. The switches are wired directly in series with the machine's power supply.
So if even one switch is not depressed, meaning, I don't know, a metal chip is trapped underneath and the part is slightly askew, the circuit remains open, and the system physically will not allow the drill to receive power.
And if you don't want physical contact with the part, perhaps it's delicate or freshly painted. Example 7 introduces infrared sensors. You fire an infrared beam across the conveyor belt right at the entry point of the processing machine.
So breaking the beam is the trigger.
Right. If the part is loaded correctly, its physical mass interrupts the beam, reflecting the light back to a receiver and closing the safety circuit. If a worker forgets to load the part and hits the start button, the beam remains unbroken, and the machine's logic controller refuses to run an empty, wasteful cycle.
But my absolute favorite example in this entire document, the one that perfectly encapsulates the brilliance of keeping it simple and fighting complex problems with fundamental physics, is example 9.
The fan.
The empty carton problem. It's a classic case study in over-engineering versus practical engineering.
Right, so you have an automated packing line placing retail products into cardboard shipping boxes. But occasionally, the packaging machine misfires and sends a completely empty, sealed carton down the conveyor belt to be shipped to a customer.
Which generates angry customer complaints and wastes shipping costs. Exactly. Now, a modern tech company might solve this by installing a highly complex load cell weight sensor, or an X-ray vision system, or an RFID tracking array to detect the empty boxes. But what is the poka-yoke solution?
You place a $20 oscillating desk fan on the side of the conveyor belt, aimed directly at the passing boxes.
It is so brilliantly simple. A full box contains product, it has mass, it weighs enough that the wind resistance from the fan does nothing, it rolls right past.
But an empty cardboard box is incredibly light. When the empty box passes the fan, the wind pressure simply blows it right off the conveyor belt and into a recycling bin on the floor.
Problem solved. Zero programming required, zero complex software maintenance, and it's 100% effective based purely on mass and aerodynamics.
It perfectly contrasts with some of the more complex trends in manufacturing today. We have a source here from the Institute of Corrosion titled, "What do Industry 4.0 and Industrial IoT mean for predictive corrosion management?"
Right, a lot of buzzwords there.
It discusses highly complex networks of internet-connected sensors, massive big data analytics, and AI predictive algorithms. And while those Industry 4.0 technologies are vital for macro-level optimization and predictive maintenance, the DESFAN reminds us that on the factory floor, simplicity is often the most robust form of engineering.
True mistake proofing is about understanding the reality of the human-machine interface in the messy physical world, not just in a pristine theoretical data model.
It's acknowledging human fallibility. Whether it's the different size guide pins, the infrared beams, or the desk fan, they don't try to train humans to be perfect, infallible robots. They design the physical environment to accommodate imperfect humans safely and efficiently.
Which brings us to a critical tension moving forward. We started this journey looking at the microscopic asperities of metal, where boundary friction is quietly draining 23% of the world's energy.
We looked at how we fight that friction with advanced fluid films and dry lubricants like molybdenum disulfide in the vacuum of space.
We examined the terrifying consequences of when an interface loses its physical resilience, like the stiffened O-rings on the Challenger space shuttle. And we explored the sci-fi future of magnetic gears and touchless vacuum couplings that eliminate physical wear entirely.
But we also found that for humans, touchless interfaces are a cognitive nightmare. We need the physical, tactile friction of a button to drive safely, and we need the foolproof physical guardrails of Poka-yoke to protect us from our own mistakes on the factory floor.
As we continue to engineer out physical friction in our machines, using magnetic levitation, touchless sensors, and automated predictive algorithms, we have to be incredibly careful that we aren't inadvertently engineering in cognitive friction for the humans who still have to operate, maintain, and understand them.
Right. The ultimate interface of the future might not be the one with absolute zero friction. The ultimate interface might just be the one engineered with exactly the right amount of friction, placed perfectly, to remind us that we are still connected to and in control of the physical world.
A perfectly engineered click right beneath your fingertip. Thank you for joining us on this deep dive. I highly encourage you, as you go about your day, to really look at the hinges, the buttons, the fasteners, and the countless mechanical interfaces in your own life. Give a little nod to the incredible physics, the unseen engineering, and the careful mistake-proofing that is quietly working to keep it all together. Take care, and we'll catch you on the next one.